In this session, we will solve some problems on the concepts which we have been looking till now. So this is our first problem, wherein the state of stress at a point is given in this form. So I can write this properly in terms of rectangular stress component or in terms of matrix as, since sigma x is 10,000, I will write it as 10,000, sigma y is minus 5,000, and sigma z is how much? Sigma z is also minus 5,000, and then this components, shear stress components, have been given as 10,000 each, right? So this is 10,000, this is 10,000, also this is 10,000, this is 10,000, and this is also 10,000. So this is what has been given, and they are asking us to determine the normal and shearing stresses on a plane that is equally inclined to all the three axes. So basically the state of stress at a point has been given to us, and then we need to find the normal and shear stress components on a plane which passes through this point, all right, which passes through this point, and it is equally inclined to this frame of reference. It is equally inclined to these three axes. So basically it's what this means is that its outward normal is equally inclined to all these three axes. Suppose say if this is its outward normal of this plane, then this outward normal is making equal inclination with respect to x, y, and z axis. So in case of direction cosines, we had seen that if there is a plane which makes an equal angle with respect to all three axes, then it happens so that its direction cosines nx, ny, and nz, they all three will be equal, and their value comes to 1 by root 3. So this is what we had seen in case of while looking at the topic direction cosines, right? So basically here now what we need to do, we need to find the normal and shear stresses on this plane. So normal stress will look somewhat like this, right? This will be our normal stress, and then this will be our what? Shear stress. So we need to find basically the normal stress, and then since it is the n plane, I can even write here n. So I need to find normal stress and shear stress on this plane. So let us do that. And we also got to know that with the help of the knowledge of direction cosines, we got to know that since this plane is equally inclined to all these three axes, its outward normal will make equal angle with respect to x, y, and z axis, and because of that these values of direction cosines nx, ny, and nz will be equal, and that will be 1 by root 3. Now in order to find this normal and shear stress, first thing what we need to do is we need to find the stress vectors in x, y, and z direction, and that can be very easily done by using what? By using Cauchy's stress equation. So basically we need to find here now what are Tx, what are Ty, and what are Tz, and we know that we can easily find this Tx, Ty, Tz by using what? By using Cauchy stress equations, right? So Tx on the n plane, by using Cauchy stress equation, we know that it is what? Sigma x nx plus tau xy and y plus tau xz and z. This is what we know from Cauchy stress equation. Similarly, what is Ty? This Ty component on this n plane, why I'm calling it as n plane? Because its outward normal is n here. So this Ty can be written as tau xy nx plus sigma y and y plus tau xz and z, and then similarly this Tz will be equal to tau xz and z plus tau, this should be, I think, yz, right? This should be yz, tau yz and y plus sigma z and z. Fine. So this is our Cauchy stress equation, and with the help of this Cauchy stress equation you can easily find what is Tx, Ty, and Tz, because this state of stress is known to us. Sigma x, tau xy, tau xz is known to us, right? It is given to us. And then also the direction cosines of this plane is known to us. It is 1 by root 3, since it is equally inclined to all three axes. So if I start substituting these values, I can easily write this sigma x as how much? It is 10,000 multiplied by 1 by root 3, plus this is how much? Tau xy is also 10,000 multiplied by 1 by root 3, and then how much is tau xz? This is also 10,000 multiplied by 1 by root 3. Now if I just do this calculation, I will get this Tx as root 3 times, it will be root 3 times 1000, and I mean sorry 10,000, and what will be the units? Since here the units are Newton per centimeter square, even this will be Newton per centimeter square. Similarly, I can find now what is Ty, and for that I need to substitute what is tau xy, which is again 10,000. Nx is how much? 1 by root 3. How much is sigma y? It is minus 5,000 multiplied by 1 by root 3. And how much is tau yz? Tau yz is nothing but this value, which is again 10,000 multiplied by how much is nz? It is 1 by root 3. Now again, if I calculate this, I should get this value as minus 5,000 times root 3, and unit will be again Newton per centimeter square. And then finally I need to find this, right? I need to find this. So how much is tau xz? Tau xz is again 10,000 times 1 by root 3. And how much is tau yz? Same thing. It is again 10,000 multiplied by 1 by root 3. And then finally sigma z is minus 5,000 times 1 by root 3. So again this value will come same as this. So this is minus 5,000 times root 3 Newton per centimeter square. So with the help of Cauchy's stress equation, we have been able to find the the stress vectors in x, y and z direction on this plane. Now we know that in order to find this normal stress sigma, we can make use of our equation. That is, we had said that sigma is nothing but the projection of this stress vector T and x, right, along sigma. So it is T and x nx, right, plus it will be again the projection of this y vector on sigma. So it will be T and y, right, Ty and y, plus this will be T z and z. And then in this case, if I substitute the values of this, so this is how much? This is root 3 times 1000 10,000 multiplied by 1 by root 3, plus it will be ty is how much? I'm sorry, this shouldn't be minus, even this will be plus, right? This will be, these values will be plus, so this will be plus 5,000 times 5,000 times root 3 multiplied by ny is again 1 by root 3. And then similarly, how much will be tz? Tz will be also 5,000 times root 3 multiplied by 1 by root 3. So everywhere this root 3 can be cancelled very well. And then finally I will get this sigma as 20,000, and units will be again same, Newton per centimeter square. So we have been able to find what is normal stress on this, right? What is normal stress on this, on this plane. But how to calculate now shear stress? We had seen that the shear stress tau square can be calculated as, and then in fact I can write here n also, because since this is the normal stress on the plane whose outward normal is n. So similarly shear stress can be found out as, it can be found out as resultant stress vector square minus normal stress vector square, right? And but what is resultant stress vector? Resultant stress vector is nothing but this resultant stress vector T will be, this t will be nothing but, in fact this tn square will be nothing but txn square plus tn y square plus tn z square, and these are the stress components in x, y and z direction. So how much is tn x square? It is root 3 times 10,000, right? So this will be root 3 times 10,000, root 3 times 10,000 whole square, plus this will be root 3 times 5,000 whole square, plus again tz is also root 3 times 5,000 whole square. Now if I do all these calculations, I will get this value as 450 multiplied by 10 to the power 6 Newton per centimeter square. So once I get this value, I can easily substitute this here, and I can write this as 450 multiplied by 10 to the power 6. This is already in terms of square, right? So I just leave it as it is, and then this will be what? This will be 20,000 square. So once I do again this calculation, finally I will get this tau n as 7,000 Newton per centimeter square. So this is how I can find normal stress, and I can find, I mean shear stress, and I can find normal stress on a plane, on any plane, if we know its direction cosine, and also if we know the state of stress at a point. In this case, this state of stress at this point was given to us, and also the direction cosine of the plane on which I need to find the normal and shear stress components were also known to us. So because with this and with the help of Cauchy stress equation, we could easily find what is normal stress and shear stress. So after this, I will go to the next problem. This is the next problem which we will be solving now. Basically, a state of stress is again given to us. So from here we know that sigma x is 9, then megapascals, it is 9 megapascals. Units are very important, all right. Sigma y is 5 megapascal, sigma z is 4 megapascals. Similarly, we have tau xy as 6 megapascals, tau xz as 5 megapascals, and tau yz as 2 megapascals, right? This is sigma x, sigma y, sigma z, tau xy, tau xz, tau yz. And then they are asking us to determine what? To determine principal stress and principal direction. Also check for stress invariants. This is also what we need to do in this problem. So to find basically these principal stresses, we know that we can find the principal stresses by writing down the cubic equation of principal stresses, right? And the cubic equation of the principal stresses can be very easily written as sigma cube minus I1 sigma square plus I2 sigma minus I3 equal to 0, where what are I1, I2, I3s? I1, I2, I3s are nothing but the first, second and third stress invariants, where I1 was sigma x plus sigma y plus sigma z. So in this case, what are our sigma x, sigma y, sigma z value? It is 9 plus 5 plus 4. So this will come to 9 and 5 is 14 plus 4 is 18. So this will be 18 megapascals. Similarly, I can find I2 as, I2 is nothing but it is sigma x, sigma y plus sigma y, sigma z plus sigma z, sigma x minus tau xy square minus tau yz square minus tau zx square. So once I start substituting these values, all these values, this will be basically what? 9 multiplied by 5 plus this will be 5 multiplied by 4 plus 4 multiplied by 9 minus this will be 6 square minus 5 square minus 2 square. In fact, this should have been 2 and then this will be 5, right? This is 5 and this is 2. Okay, so once I start solving this, I will get this value as 52 megapascals. And what about I3? I know that I can write this I3 very easily in terms of determinant. It is nothing but the determinant of a rectangular stress components, right? So this I can easily write as this, right? This is nothing but the determinant of rectangular stress component. So this will be again tau xy, tau xz, tau yz. And then if I substitute all these values here again, basically these are what? 954, 954, and then I have here 6, 5 and 2. So this is 6, 5 and 2, right? 6, 5 and 2. This is what actually the matrix which is given to us, rectangular stress component or state of stress at a point. So if I just take the determinant of this, I will get I3 as 27 megapascal. I hope you all know how to take determinant on your calculators. So with this I will get the values of I1, I2 and I3. The moment I get the values of I1, I2, I3, now we can very easily determine the principal stresses. We know that the equation of principal stress is sigma cube minus I1 sigma square plus I2 sigma minus I3 should be equal to 0. But then sigma cube minus what? How much is I1? I1 is 18, right? So I'll substitute this as 18. How much? Then this is sigma square. How much is I2? I2 is 52. So I will substitute this as 52. And how much is I3? I3 has turned out to be 27. So this will be minus 27 equal to 0. Now again you can substitute. You can input this, you can put this equation in your calculators, and you will be able to find three values of this cubic equation, and that will be 14.554. You will also get one more value as 2.77, and you will get a third value as 0.667. So basically, how do we arrange these values? The highest value we will call it as sigma 1. Then the second highest value I will call it as sigma 2, right? Sigma 2 will be equal to this. The units are MPa, right? The units are MPa. And sigma 3 value I will call it as this, MPa, because we always give call sigma 1 is the highest value out of these three, and sigma 3 is the lowest value out of this three. So basically I have been able to determine what is sigma 1, sigma 2 and sigma 3. So these are our three principal stress values for this stress component or for this state of stress. Now once this is done, we know that now each principal stresses will have the principal planes associated with it, right? For example, if this is the plane of first principal stress, then the plane of second principal stress might be somewhat like this, right? And the plane of third principal plane will be somewhat like this. They will be, all three will be mutually perpendicular to each other. So basically this will be our three principal planes, right? This will be our three principal planes. So sigma 1, for sigma 1, let us say this is the plane for sigma 1. So this is the plane for sigma 1. Then the second plane sigma 2 may be for this, and then the third plane sigma 3 may be of this. So these are the three planes. Now of this, all these three planes, we can find its orientation with respect to our x, y and z axis. So the orientation of this plane with respect to x, y and z axis can be given as nx1 and y1 and nz1. Similarly, the orientation of this plane can be given as nx2 and y2 and nz2. And basically this nx and y and z are nothing but the direction cosines, right? So, and then the orientation of the third plane, this plane can be also given as nx3 and y3 and nz3. So let us see now how to find this direction cosines for this each principal stress. So let us consider this now, first principal stress. I will consider this first principal stress. So its direction cosine should be nx1, ny1 and nz1. So for this what I will do, I will again consider this matrix here. I will consider this, this determinant of state of stress. So the determinant of state of stress was what? 9. Then we had here 5. Then we had here 4. Then we also had what? 6, 5, and then this was 2, and then we had here 6, 5 and 2. So since we are now finding the direction cosines of first principal stress from this normal stress values, what I will do is I will subtract the value of sigma 1. I will subtract the value of sigma 1 from all three normal stress components. Why? Because at present I am trying to find the nx, ny, nz or the direction cosines for first principal stress, or I am trying to find the direction cosine of first principal plane. Because of this, what I will do, I will subtract the values of sigma 1 from all three normal stress components. Okay, now once this is done, let me just simplify this. So if I substitute the value of sigma 1 as 14.55, I will get this matrix as what? I will get this determinant as minus 5.554. Then this will be minus 9.554, and this value will be minus 10.554, and this shear stress components remain same, right? 6, 5 and 2. Okay, now after doing this, what we will do is we need to find three terms called as A1, B1 and C1. Now how to find A1? Now in order to find A1, what we will do is we will neglect the first component, the first row and first column, and whatever remains, that I will put it as the terms of A1. So now what is remaining now after this? The terms which are remaining after neglecting first and first column is minus 9.554, and I have here minus 10.554. These values will remain as it is. Now I need to find one more term b1. I need to find one more term b1, and then this b1 can be found by neglecting what now? I will now to in order to find b1, I will neglect this first row and then second column. I will neglect the first row and second column. So what else, what is remaining now with me after neglecting first row and second column? The values which remain with me are now 6, 2, 5 and minus 10.554. Now similarly, to find C1, now what we will do is, in this case, to find C1, we will neglect again first row and then now third column. Now whatever is remaining, this I will put it here. So these values will be 6, 5 minus 9.554, and I have here 2. Okay, once we find all this, then I need to find the determinant of this A1, which will be nothing but this will be 96.83. Similarly, determinant of this B1 will be minus 69.325, and determinant of this C1 will be 40.662. Now after this we need to find one more quantity, that is the value of root of a1 square plus b1 square plus c1 square. And if I find this value from these values of a1, b1, c1, I will get these values as 125.838. Now after doing this, now our task will be very easy. In order to find the direction cosine of first principal plane nx1, we will find it as nx1 will be equal to a1 divided by root of a1 square plus b1 square plus c1 square. So this is basically nothing but 96.83 divided by 125.838, whose value we will get it as 0.767. Similarly, value of ny1 will be b1 divided by root of a1 square plus b1 square plus c1 square, which will be equal to minus 69.325 divided by again 125.838, which will be equal to 0.5508, and of course this sign should be minus. Similarly, nz1 can be found as, now it will be c1 divided by root of this value a1 square plus b1 square plus c1 square, which is nothing but it is equal to 40.662 divided by 125.838, and this value will be approximately equal to 0.323. So these are basically the direction cosines of the first principal plane for the stress sigma 1, and that is why everywhere the suffix 1 has been put, right? Everywhere the suffix 1 has been put, just to show that this nx1 ny1, I mean this nx ny nz values are for the first principal stress sigma 1. Now how to check if these values are correct, how to cross verify or how to check if these values which are obtained of the direction cosines are correct? And for that we know the property of direction cosine, that always nx square, right, the sum of this square of direction cosines should be equal to what? It should be equal to 1. And then if I substitute these values, 0.767 square plus minus of 0.5508 square plus 0.323 square, one will observe that this value is approximately equal to 1. So this is how we can cross check if our values of direction cosines are correct or no. So this is how we can find the directions cosine of the principal planes. Now this is the story of finding how to find the direction cosine of first principal stress. In case if I now want to find the direction cosine of second principal stress, what I will do is, from this normal stress components, I will subtract what now? I will subtract sigma 2 value, right? I will put sigma 2 values, and then in place of a1, b1, c1, I will write those values as a2, b2, c2, just to indicate that these a b c terms are for second stress, second principal stress. And then once I get values of a2, b2, c2, I will find this term a2 square plus b2 square plus c2 square. And then finally nx2, ny2, nz2 will be found as a2 divided by this term, b2 divided by this term, c2 divided by this term. Alright, and then again you can cross verify this. This I won't be doing for second and third principal stress. You may please do it from your side. Now there is one more thing which we need to see. They are asking us to verify whether I mean to check for stress invariants. Now from this formula we got that the stress invariants are how much? 18, 52 and 27. But we also know that the stress invariants can be also found in terms of principal stresses, right? And how do we find that? We know that I1 can be found as sigma 1 plus sigma 2 plus sigma 3. I2 can be found as sigma 1 sigma 2 plus sigma 2 sigma 3 plus sigma 3 sigma 1. And how do we find I3? It is product of sigma 1 sigma 2 sigma 3. Now if I try to put these values in terms of principal stresses, one will observe that these values comes exactly same as that of, I mean if not exact, but at least it will be very close to these values. In fact, it should be exact. All right, if we don't take all the decimal points, then it might be not be exact, but it will be always very close to these values. So this will be almost equal to 18. This should be almost equal to 18. This I2 should be almost equal to 52, and this I3 should be almost equal to 27. You may try it. All right, just substitute the values of sigma 1 sigma 2 sigma 3 here, and then see the values, check the values of this i's or the invariants, and then we are done with our problem. Let us solve one more problem, and this will be the last problem in this video. So here basically what is given to us is again the rectangular stress component is given to us, and then this is basically a problem of the stress transformation of stresses. So what basically they are saying is, for this XYZ frame of reference, this is our XYZ frame of reference, right? So for this X, Y and Z frame of reference, this is the rectangular stress component. Suppose if we have one point here, then across that point, this will be the rectangular stress components. Then, then we need to show that by transformation of stress, the stress components when the axes are rotated by 45, I mean rotated by 45 degree about the z axis. So basically what we need to do, if we rotate this axis by 45 degree about the z axis, we need to find what will be the transformed stress component, or what will be the transformed stresses. All right, so basically what we need to do initially, what we will do, we will rotate this this axis by 45 degrees about z axis, fine. And to do that, what we can do is, I can draw here x axis, and this will be now x dash. Let the transformed axis be called as x dash, and then the transformed y axis will be called as y dash, and the transformed z dash will remain on z, right? Because what we have done, we have basically rotated this axis about z axis, right? We have rotated this axis from here to here about z axis. So z dash will be on z, right? And how much is this angle? This is 45 degrees, and even this is 45 degrees. So basically, in order to find tau ij dash, we know that we want a transformation matrix A. Then we already have tau ij, the original tau ij, or the stress component with respect to x, y, z axis, and then I want the transpose of transformation matrix. And then how do we find this transformation matrix? We know that the transformation matrix is given as what? L1, L2, L3, right? M1, M2, M3, and this is N1, N2, N3, where what are L, M and N? They are nothing but cos of angle between the transformed axis and the original axis. So what was L1 here? L1 was, if I draw that table again, if this is our x, y and z, and this is our x dash, y dash and z dash. So what was L1? L1 was the angle between x dash and x. L2 was the angle between y dash and x, and L3 was the angle between z dash and x. Similarly, we have M1, M2, M3, which are nothing but the angle between x dash y dash y, and z dash y. Similarly, I have here N1, N2, N3. So this is what we had seen last time in our last video when looking at the theoretical aspects of this transformation of stresses. So basically L1 is nothing but it is a cos of angle between x dash and x, right? So how much is the cos of angle between x dash and x? The cos, it is nothing but L1 is cos of angle between x dash and x. And how much is the angle between x dash and x? It is 45. And cos of 45, I know it is what? 1 by root 2. So this 1 by root 2 is nothing but 0.707. So let me write this as 0.707. Okay. How much is L2? L2 is nothing but it is cos of angle between what? Y dash and x. Now how much is the angle between y dash and x? See, the angle between x and y is 90, but further y dash is 45 degree to y. So basically the angle between y dash and x will be 90 plus 45, which will be 135, and this will be minus 1 by root 2. So basically this is minus 0.707. So this will be minus, I mean this value, right? This value will be minus 0.707. What about L3? L3 is the angle between Z3 and X. How much is the, I mean Z dash and X. How much is the angle between Z dash and X? It is 90, right? The angle between Z and X is 90, and Z dash just happens to be passing through Z, right? So basically the angle between Z dash and X will be 90. And how much is cos of 90? We know that the cos of 90 is nothing but it is 0, right? Cos of 90 is 0. So this will be 0. Okay, we have been able to find this. Now what about M1? M1 is what? Cos of angle between x dash and y. How much is the angle between x dash and y now? The angle between x dash and y is 45, and cos of 45 is, again it is 0.707. Angle between y dash and y, again it is 45, so 0.707. And now cos of angle between z dash and y will be 90, angle will be 90, so this is basically 0. Okay. Now, the angle N1, angle between what? N1 is what? Angle between cos of angle between x dash and z. Cos of angle between x dash and z is still 90 degree, right? Because this x dash and y dash are in xy plane itself, because we had rotated it about z axis. So angle between, since the angle between x and z dash, I mean, since the angle between x and z is 90, therefore the angle between x dash and z will be also 90. So cos of 90, n1 is nothing but n1 will be cos of 90, which will be, again it will be 0. Similarly, n2 will be again angle between y dash and z, which will be again 90, and this will be 0. So finally, what about N3? N3 is nothing but it is cos of angle between Z dash and Z. And how much is the angle between Z dash and Z? N3 is cos of angle between Z dash and Z, which is angle between Z dash and Z is 0, because basically they both pass through same line. So this will become 1. So finally, I have been able to find the transformation matrix. Once I get the transformation matrix, just substitute it in transformation equation. So basically, my equation will be now, it will be tau ij dash, it will be equal to my transformation matrix 0.707 minus 0.7070, and this is 0.707. And please remember that this is not a symmetric matrix, all right? Sometimes we do mistake thinking that it is symmetric matrix. In fact, see here itself it is not symmetric. Here I have got minus, here I have got plus value. So this values totally depend upon how is the rotation that is taking place with respect to the original axis. Okay, then the actual tau ij was what? 412,068, and this is 120, right? This is the actual stress matrix with respect to original axis xyz. And then I need to take the transpose of this. So transpose of this will be basically, this will be 707 minus 0.7070, right? This will be 0.707, 0.707, and this will be 0. And this will be how much? It will be 0, 0, and 1. Okay. So once I get this matrix, what we know that I can easily substitute this matrix in our calci, right? I can just input these values in our calculator and I can carry out the matrix multiplication of 3 by 3 matrix very easily on Casio, even on Casio FX991 series, right? I can very easily do that. And once I do this, one will observe that the value of after multiplying this will come to how much? It will come to 5.9980. This value will be 0.9996. This value will be 1.4140. Similarly, this will be 0.9996. This will be 3.9987 and this will be minus 1.4140. Similarly, this value will be 1.4140. This value will be minus 1.4140 and this value will be 8. Now, since this is a rectangular stress component, since this is a rectangular stress component, right? This is again a rectangular stress component, but for a different frame of reference. After the frame of reference was rotated with respect to the original frame of reference, but it is a rectangular stress component, and therefore this matrix has to be a symmetric matrix, right? This matrix has to be a symmetric matrix. So I get this as a symmetric matrix. All right, I have found the now the stresses when the axis is rotated 45 degrees about z axis, but also I need to find now the stress invariant with respect to new frame of reference and show that the stress invariants remain unchanged. So basically what he is asking us to calculate I1, I2, I3, then to calculate I1 dash, I2 dash, I3 dash, and prove that I1 is equal to I1 dash and so on. Okay, we know this, right? These individual values will never be equal. Sigma x dash will never be equal to sigma x. I mean, in general cases, sigma y dash will not be equal to sigma y. Sigma z dash shouldn't be equal to sigma z. But in this case, these two values are coming same. That is fine. Sometimes it may be equal, sometimes it may be not equal. But it is not that always these values should be equal to this. Similarly, these values are not equal. These values are not equal. Individually, these terms sigma x is not equal to sigma x dash, sigma y is not equal to sigma y dash, and so on. Tau xy shouldn't be equal to tau xy dash, and so on. But what will be equal? Its invariants will be equal. That is what we have been discussing till now, right? So basically that is what we need to prove. Now if I calculate I1 for my original component, I get it as 4 plus 6 plus 8, right? Sigma x plus sigma y plus sigma z. And how much this value is coming to? 8 plus, I mean 6 plus 4 is how much? 10 plus 8. So this is coming to 18 megapascals. And then what about I1 dash? This is nothing but sigma x dash plus sigma y dash plus sigma z dash. So basically from here I get this as what? 5.9980. 5.9980 plus how much is sigma y dash? 3.9987, right? Plus 8. So it is almost equal to 6 plus 4 plus 8, right? It's almost similar to this. So this will be equal to 17.996, which is approximately equal to 18 megapascal. So basically I got I1. What from here what I can conclude? I can conclude that I1 is equal to I1 dash. Now similarly we will find I2. How much is I2 now? I2 is what? We know that I2 is what? Sigma x sigma y plus sigma y sigma z plus sigma z sigma x minus tau xy square minus tau yz square minus tau zx square. And this value from here we'll be able to find it as around 99 megapascals. All right, but from these values, that is sigma x dash sigma y dash plus sigma y dash sigma z dash plus sigma z dash sigma x dash minus tau xy dash square minus tau yz dash square minus tau zx dash square. From these values one will be able to calculate the I2 dash, and that value will be approximately equal to 98.9596, which can be approximated as 99. megapascal. So again, we what we get from here is I2 is equal to I2 dash, right? This is what we know. This invariant should be equal irrespective of the frame of reference, right? This invariance has to be equal irrespective of frame of reference. But here what we are doing, basically we are just verifying them. All right. What is I3 now? I3 should be determinant of this, and I3 dash should be determinant of this. And then upon finding the determinants, one may find that I3 is 159.895 I3 dash, and I3 can be approximately equal to 160 megapascals. So basically from here again we get that I3 should be equal to I3 dash. So this is what we have been studying till now, that the stress invariance will remain same irrespective of what is the frame of reference, but the individual values of sigma x may change, sigma y may change, sigma z may change, similarly tau x may change, tau tau xy may change, tau xz may change, tau yz may change, and so on, but its stress invariance will remain same.